Let's get ready for physics, huh? We're going to do some problems that you will, if you're going to take, what's it, 105? Ooh, you're going to do a problem just like these. You're going to have to get this understanding going. Even if you're going to 205, you most certainly need to know these concepts. Let's do just a couple of old classics. Actually, stole them straight from your text. Maybe I'm just hoping that maybe when I explain it's a little better than just reading it out of your textbook. So this is just straight off of page 285. It's example 10 and example 11. Shows me it's easy to copy and paste and show you some pictures. So here's our first one. It says that we want to find the component form of the vector that represents the velocity of an airplane descending at a speed of 150 miles per hour at an angle of 20 degrees below the horizontal. Well, if we're thinking about this, now here's our XY graph. Right? You always want to place this thing, the vector coming out right at the origin. So you can look at the vector. And it's kind of weird to think of it as speed is a length. You know what I mean? But velocity has two components. It has both speed, it's got magnitude and direction. It's got speed and what direction are you traveling in? So those are the two pieces that get put together. Now we can see if, now by context it doesn't really make any sense, but the way we have it set up, this is going into the third quadrant where both our x values and our y values are negative. So we should expect that we have some negative values inside of here. That should make sense. It's just telling us it's pointing in that direction. We could have had it set up. We could have drawn it in another way and just said it was descending like this. You know what I mean? We could have, but it didn't. So the picture is super nice because it's telling us that it's descending at an angle of 20 degrees below the horizontal. Would you just throw 20 degrees into one of these problems and not recognize that if we're going in this direction, this is actually going to be 200 degrees. That's 200 degrees, not 20. It's just by the way you set it up, or you'd have to set it up as 340 degrees if we were traveling in that direction. All right, neat. So what are we trying to do? We just want to find the component form. Cool. So what this is doing is it's actually giving us one of these. Here's our magnitude is equal to 150 because that's the speed. Speed is in magnitude. Velocity is a vector. And then we need to find the angle. And it tried to trick you in the problem by saying 20, but it's not 20, right? It's going to be that 200 right there. 200 degrees. So we're given an angle and we're given a magnitude. Now I'm going to run through and do this for the exact answer, show you what that is, and then we'll punch in at the end and we'll make certain that we get our rounded answer. And I'll give you the same thing as what the book does. It takes it to 2 decimal places. Let's tackle it. So we know that our vector v is equal to, what was that thing again? We could say that it's going to be the magnitude times cosine of the angle, comma, the magnitude times sine of the angle. 200 degrees. And there it is. But we already got the freaking magnitude. Let's go. What are we worried about? Let's jump into it. So we say that here's our exact answer. 150, because that's what the magnitude equals, right? We just took this. This equals 150. Call it 150. Let's get rid of this bull stuff. All right. Times, we got that 150 times cosine of that 200 degrees, and then 150 times that sine of 200 degrees. Sorry if I didn't finish my train of thought. My dog got up and I had to pause it. I think I lost what I was trying to say. So here's an exact answer. It's exact. It's perfect. There's nothing wrong with this answer whatsoever. But it doesn't really tell us anything. You know what I mean? It doesn't tell us anything, so why don't we go put it in and we're going to go approximate it. And this is just straight from your text. They had that thing into, like, isn't cosine negative in the third quadrant? So that would have given you a negative value, and you multiply it by 150. You get negative 140.96. And then when you multiply the 150 by the sine of 200, sine's also negative in the third quadrant, so that should make sense too. That we're going to say that this is negative 52.30. Now, we can really break this thing down. Oh yeah, let's write this in the real weird form. Oops. Let me give this squiggly. This doesn't actually equal that, right? Write it in the other form. I hat minus 52.30. J hat. Yeah, so we got this thing in there. But what that is saying, let's really kind of give it some thought. Because we have to know what it means moving forward. So the I hat is the horizontal component. That's the horizontal component. So what it's saying is we're actually traveling in the horizontal direction. And the plane is, not us, is 140.96 miles per hour in the horizontal. So if you were trying to go horizontally, you're not going quite 150 miles an hour. You lost a little bit of the speed because it's actually going toward, or speed, speed. Going towards going down. But also as we're descending, well, we're losing value too. So it's saying we're actually, the vertical, we're going at 52.30 miles per hour down, or we're going to call it negative. So it's negative 52.30 miles per hour. So we can break it down into individual components where if you give us the angle and you tell us how fast something's going, I can tell you exactly how fast it's going in the horizontal or the vertical, and you can too. So there's an application of the same problems that I told you we were going to need to know how to do, just in an application. And now let's do an old classic. A force of 600 pounds is required to pull a boat and a trailer up a ramp inclined at 15 degrees from the horizontal. Find the combined weight of the boat and the trailer. This is the big one. Let's keep looking into this, and everything has to do with the picture. So we have a 15-degree horizontal. That's from right in here. We're at that 15 degrees from the horizontal. But there's such a way that we're going to set this weird-ass triangle up every time. There's this weird triangle down here that pops out. Now, the reason why we're going to create it in such a way, I know there's so much going on, but we just kind of go, at least for me, I got the thing just memorized and then slowly but surely started to understand actually what it meant. So we can create a triangle below it that has the same angle. Those two match what's in yellow. I know it might be a little tough to see and it's harder for me to highlight on this. But those are going to be the same things. Now, there's going to be a couple of pieces. Now, I'm just going to label them with a little bit of color and just say that our length on this one, this length here, that length there, we're going to call that one G, because it's going to be our, let's call it the magnitude of G, is just equal to the force of gravity. Okay? Now what this one is this one that's facing down from B to C here. I'm going to call this one, you know what? What do I want to call it? I'm going to call this one F, because why not? I shouldn't use that one. But it's the force. This thing, the magnitude of F. Oh, these need hats on them because they're vectors. This F is just going to be the force against the ramp, right? Isn't there going to be some force that's pushing down? Remember that Newton talked about equal and opposite? So since that's at an incline when it's pushing on the ramp is actually pushing back at it. I don't know if that's pushing, but it's the equal and opposite force, which is going to go perpendicular or orthogonal to this line right here, pushing back against. So this force is going down, the force of the boat on the ramp, and so that's the force against the ramp, right? Because it's facing down, right? This one that's facing with this little arrow, it's facing down. So that's the boat pushing down, and the trailer, of course. And then the last thing we have is the little guy right here, and I'm going to call this one A. You know, I'm going to call it little a. Let's call it little a, because let's call it little q. And little q's magnitude So it's given in the frickin' question. I used to call it Q because it's in the question. And that was, the force required to pull boat. But we already have that. That's given as 600 in our problem. 600, what did it say? 600 pounds is required. By the way, pounds are a force, and they are a vector. So that was given to us, that Q is equal, or the magnitude of Q is 600 pounds. Oh, maybe it's not a force. I don't know. So why don't we go get after this thing, and let's take this right triangle that was created. I don't know what we're calling this one our Q, but actually we better give it some magnitudes to it, because these are lengths we're talking about. The force against the ramp. And then we have that force of gravity, and that gravity is always going to be your hypotenuse in these sorts of situations. Well, we already know a little something about the force of gravity. We would need to be able to put that in, but let's not even mess with it. We're given an angle right inside of here. I don't want to talk about that. We have this angle, 15 degrees, right inside of there. And we already know Q, so why don't we get rid of this sucker, and we're going to call this one 600. Now we have a squared plus b squared equals c squared. So we have, oh, no, that's not going to work. Shit, we only have one of the lengths. I think we might want to look at our right triangle and going, well, look, what do you want to solve for? I think I'm going to go get it. Oh, shit. I was supposed to have something like this. I think I want to go get this one here. The magnitude of that gravity. What was that force that's being applied? I think we could do that because if we have our opposite side, right? Oops, I gotta stop doing that. We got our opposite side and our hypotenuse that we're looking for. I think that's sine. Let's set it up and we can say that sine of 15 degrees is equal to that 600 over what we're looking for. Oh, that's just the gravity. Well, the gravity doesn't help us much. We wanted wait. Let's do some fancy footwork to this thing. We multiplied it over, we divide it out. Hopefully you know this trick, and we get sine of 15 degrees. And we punch that thing into a calculator. Like, oh, there it is. 2,318-ish. Well, do you know that this is actually, that's the combined weight of the boat. This gravity, the magnitude of the gravity. It's actually coming back. It's telling us gravity is acting upon this sucker. Now, how does gravity affect your weight? Does it pull it to the side? Does it yank it to the left? Well, I think that's called momentum and not the gravity. Gravity yanks you straight down. So when we're looking at this problem and it's talking about the combined weight of the boat and the trailer, we are 100% talking about what is that force of gravity upon the boat and the trailer. And that's what we're going to call the weight. So really for the answer to this problem we just had to find the magnitude of this G bar, the force of gravity acting upon, well, actually this is the magnitude of the force of the gravity acting upon the boat and the trailer. And we can say that our answer is 2,318 pounds is the weight of the boat and the trailer. These things are wonky, they're weird, and I probably did a horrible job of explaining it. I'm a math teacher, not a physics teacher. I barely understand what's going on, but I do get the math and understand what a damn triangle is. But when you're looking for the combined weight, or you're looking for the weight of something, you're going to want to think about that. The vertical component is going straight down, right? It's not going left to right. So hopefully that was helpful. Maybe I made things worse. But that's it.